Let's apply this method of perfect squares to this circuit that we had at the beginning of today. If we look at it, that's what we want, and that is what we've just had. The perfect square, s plus a squared, plus or minus some remainder. So that's in the form of what we've just been writing, a quadratic. So in other words, we're going to use the method of perfect squares to rewrite this quadratic equation as a perfect square plus or minus some remainder, which will be our omega squared here. And so we start off by taking this quadratic, 10s squared plus 0.1s plus 1, and apply the method of perfect squares to it. And then see what we end up with, and that will give us our values for a and omega. So let's take this quadratic, just this bottom part, and focus on it. So here's our quadratic, 10s squared plus 0.1s plus 1. What's the first thing to do with it? Yeah, divide by 10 to get rid of the 10 in front of the s squared. So we divide by 10, that's the first job. If s squared is not on its own, we've got to make it on its own. S squared plus 0.01s plus 0.1. That's the first job. And now we halve the coefficient of s and square it to make the perfect square, and then see what remainder is required to get us back to 0.1. So I'll just pause this while you have a go. So we take our 0.01 and we half it and square it, and that gives us 0.4025. So I've got to add 0.099975 to get back to the 0.1 again. So that's my remainder. So I can now rewrite this as s plus 0.005, which is half of 0.01, all squared, plus 0.099975. So if we go back to our original circuit, IS, we can now write IS as equal to 1 over whatever that perfect square was. S plus 0.005 squared plus 0.099975, if I remember correctly. That's not quite the end of our problems though, is it, however, because if we look at this, and we'll want to get to this. So we've got our s plus a, we know what a is now, it's 0.005. But what about this? Omega squared, well we know what omega squared is, it's this. So how do I get omega? I square root this. But we've got this problem because on top, for this to work, on top should be omega, and at the moment we've got 1, so we're going to need to think about that too. And so what we do now is we say, okay, let's find out what omega is. So omega is the square root of 0.099975. Which is, so omega turns out to be 0.316 to 3 significant figures. So we need this to be 0.316. Whoops, 0.316, because that's what omega is. So what we need to do is to multiply top and bottom of this by 0.316, and we've got it. So what we end up with is, and I can extend the page quite easily, you might be struggling a bit here, I'm afraid. We've got the IS equals, and I'll write it out so that we can see it hopefully. 1 over, which is what we had before, this, it's s plus 0.005 squared plus 0.99975. So that's that, and that's the omega squared bit. And so we just found out what omega is. So omega needs to be on the top here. This needs to be 0.316. So we multiply the top by 0.316 to make that 0.316 on the top. But that means we've also got to divide it by 0.316. So we put a bracket around it and we write this. We multiply top and bottom by 0.316 effectively. Bit awkward when you see it. Let's have a look at it. What I do is I say, right, I've got to compare this with this. That's my comparison. So this number here that I've worked out by using the perfect square method, the 0.099975, is omega squared. So I know what omega squared is, and I know what A is. A is 0.005. So I've got those two. The only problem is this needs to be omega on top. And so what I do is I square root the 0.099975 to get omega, which is 0.316. So then I multiply top and bottom of my fraction by 0.316 effectively. So tidying it up, I get this. 1 over 0.316 times this. And this now is in the form I want it. It's omega over omega squared, and that's A. So I now know what A and omega are. And I can go back to this, and now I can do my transform. I can now say that IT, the current, is this, and I can plug in my values for A and omega. And so I can write that IT equals 1 over 0.316, I mustn't forget that, e to the minus A, which is minus A, minus whatever A is yet, minus 0.005 t sine omega t. And omega is 0.316. And there's my function that I can now map out, and it will model this circuit, the transient period of this circuit. IT, of course, if what is 1 over 0.316? What is it? Just checking. 3.16 e to the minus 0.005 t sine 0.316 t. If t equals 0, what's the current? If t equals 0, then that's gone. The side of 0 is 0. Oh, in fact, yeah, if that's 0, then in fact it will all be 0, won't it? Yeah. Let's plot this and see what we get, okay, on autograph. I'm now going to type this into autograph and see what it looks like. I'm going to type y equals this and see what comes out, and that will be the model of our circuit. No. One of the things I've not mentioned about Laplace transforms, actually, from going right back to the beginning when we talked about the transform being in replacement of an integral, the integral is taken between 0 and infinity, so actually nothing before 0 is taken into account. So we completely ignore the mathematical function to the left of 0. It only comes into reality for us as a model to the right hand side when t is positive, time is positive, in other words.
There's a link between we're talking about modelling the circuit.
So if we look at this circuit now, and we can see that we've got a decaying sine wave, and that will model this circuit, and we can come up with an idea of how long it would take for this circuit to decay. It's a bit of an odd circuit because if we look back at the original values, we had some pretty big values for the inductance, I think. So yeah, it's going to take it a long while for this to die out, and in fact this model is telling us that 400 seconds and it's still not settled down. So it's a long transient period, but it will eventually settle down to zero.
Yeah.
So that's the model for our circuit. So let's just have a quick recap on this. So what did we do? We drew our Z, our impedance for the whole circuit, express it as a fraction, put it into Ohm's law to get this. And then we recognized that this actually is a quadratic function, and so we're going to have to use this, which is in the form of a perfect square. So what we now do is use a method of perfect squares to find out what this is in terms of a perfect square and a remainder. And the number inside the perfect square gives us A, but the remainder gives us omega squared. So we have a little bit more work to do. We've got to find out what omega is by square rooting it, and then multiplying top and bottom by that number. Okay? And that's the method. So I'll stop there, and now I'll give you another example to have a look at.